Let's start with a brief recap on probabilistic mapping and configuration space. So the last module has been about how can we create consistent and reliable maps. We need those to localize and navigate. And we showed that really localization needs to be perfect, otherwise you get something like this. Here you see the odometry error building up after the first right turn. And to the right you see that there are a lot of noisy measurements, and this becomes particularly problematic when you have a robot where the laser hits the ground as the robot turns or accelerates or brakes. So we talked about techniques to get rid of that, in particular the probabilistic map. Here the idea is that the grid is containing probabilities that a cell is an obstacle, and the idea was, instead of using Bayes' rule or anything complicated, to simply say whenever the laser hits, the probability that this is an obstacle increases by 1%. And we can then introduce some kind of cutoff when an evidence threshold is met and essentially treat that part of the map as obstacles. We have then talked about how to use maps for navigation and introduced the idea of the configuration space for navigation. The configuration space of a robot is the degrees of freedom that it can have. In this case, we consider this robot to be at an XY position. And the tether orientation, the third degree of freedom, doesn't matter because the robot is circular. So the configuration space of this robot is 2D. And once we grow all of the obstacles by the radius of the robot, we can reduce the robot to a point in the configuration space and thereby navigate through the obstacles. For example, if the configuration space is free, at least 1 pixel between these two obstacles, then the robot can pass through. We also introduced a heuristic to expand the obstacles using an operation called convolution, where you take a kernel, a square quadratic kernel, and sweep it over the obstacles, thereby growing them. It's the same as a blurring operation, and after thresholding you would be able to turn a map like the one you saw earlier here into a map like this, where the navigable areas are clearly discernible and other areas are not navigable anymore. So you cannot go through these two obstacles, which are these two obstacles in practice. We also introduced the idea of multidimensional configuration spaces. This happens in the mobile robot example when the robot is not circular anymore. Now the robot is rectangular, and if it is turned like this, 0 degrees, it can go through the narrow passageway here. But if it turns 90 degrees, this is not possible anymore. If it is turned 0 degrees, then it can barely slide through the narrow passageway down here. If it's turned that way, this one becomes very broad. Now, how do you go back and forth between those two maps? Well, once you turn the robot, or moving up and down is turning the robot, and I have a representation like this here. So I have 0 and 90 degrees, and then 180 and 360 is the same. I can now move along the map with 0 degree orientation until here. Then I turn the robot. That allows me to jump to the other map and keep moving on that map. Now the question is, what is the degreezation you should choose here? This is up to you. You can have 8 different degrees, or you can have 360 different degrees, but it really also depends on the granularity of your original map. Because if you introduce a convolution kernel, then let's say you have a 20 by 20 kernel for representing your robot orientation, and there are only so many different kernels that you can use when you rotate a rectangular robot in a 20 by 20 pixel square. All right, so this was just a little recap to ground what we want to do today. We want to take navigation to the next step and want to move on from line following. This has been very helpful to study odometry and things like this. Now we want to replace line following with putting what we call waypoints in front of the robot and have the robot follow them one after the other. In practice, waypoints is really what robots would do. So an autonomous car might use a topological map to travel from one node to the other, which are the intersections of this road. But once you are on the road, you want to put waypoints in front of the car to determine the trajectory that the car should take. And in case there's an obstacle, like here, there's some random obstacle on the street that we see in our, let's say, radar sensor, we want to recompute the trajectory, put different waypoints down, and change the trajectory of the car. We teach this first before talking about how to create the waypoints, because you can easily experiment with putting waypoints down yourself and figuring out how to implement the controller. And then later we will talk about how to do path planning. All right, so if you have a car, what are you going to do? You have 2 degrees of freedom here. You can accelerate and brake. That's 1 degree of freedom. And you can steer. And I just want to get you into the right mode of thinking, looking at these examples here. So the car is currently driving 55. And what do you do when you see a speed limit of 40? Well, you will probably get off the gas and quickly let the car come down to 40. But if you see a speed limit of 25, you will actually slam on the brakes because you are quite too fast, like 30 miles per hour too fast, more than double the speed. So what you do is you actually do the math and subtract your current speed from the set speed, and you change your behavior basically based on the magnitude of this error, as we call it from now on. The last example is 55, which is the speed you currently have. And what you do there is you will use very light gas and brake, most likely, to enforce your traveling speed. The other degree of freedom is your steering. In this case, you have to do a right turn. And also here, you will turn more if the error is big and turn less if the error is small. It also depends on the speed you actually drive. We will not get into this. But what I want you to take home from this slide is the difference between what you should do and what you currently are doing is what we call error, and your behavior should be a function of the magnitude of that error to compensate for it. All right, in Webots we will use ping pong balls that we will drop at different locations to be stand-ins for the waypoints, and so you can see how the robot should drive. In this case, you see that the world coordinate system is aligned with this little coordinate system in the corner here. And you can see that the robot would need to do a right turn to drive to this obstacle. Now, how many degrees does it need to turn? We look at the x-axis here and we see it's about a 45-degree angle. But then we also have to add the current orientation of the robot to it, which is maybe 20 or 30 degrees to the left. So the total angle here that the robot has to turn is around 65 degrees. Now we can make a better drawing for this and look at the geometry of this problem. First, I'd like you to remember the right-hand rule. Like in this case, you can take the first right-hand rule and look at where the z-axis is coming. It's coming out of the picture. You can then use the other right-hand rule and see what the direction of positive rotation is. So you see the positive direction here is counterclockwise. So this is actually a positive angle that the robot has to turn. How do you compute it? You look at the x-axis of the world, which goes parallel here, and this creates a triangle. And now you can use the Pythagorean theorem. This square plus this square is that square. And from that, we can compute the Euclidean distance rho by looking at the difference in x values and y values. Similar, we can look at the angle here and compute it either using the cosine and the newfound hypotenuse, or we can actually use again the difference between y values and x values and use the arcus tangens. Finally, we have an error, which is the final orientation of the robot, which is given by its current orientation and the final one. And at some point, the robot will need to turn to not only be at the desired position, but also look the right way. Now there are two things that are different than from what has been previously said. So the first thing is I also add another or subtract another angle, which is theta r, which is the actual orientation of the robot. So in this case, the orientation of the robot is minus, let's say, 30 degrees. Why minus? Because the x-axis is here, and this is clockwise is the negative direction of rotation based on the right-hand rule. So in order to get this total angle here, I have to add what I get from the arcus tangens, and then I have to subtract the negative value that is adding this value theta r to the result, and that gets me alpha. Now, why did we take arcus tangens 2 and not arcus tangens? The problem with the tangent function is that you only get results from minus 90 to plus 90 degrees. So you only get half of the possible workspace of the robot. In order to get results from minus 180 to plus 180, you will need to use the arctang2 function. So you can see this here. This is the inverse tangent, and it goes from minus 90 degrees to plus 90 degrees. And now we introduce this function here, which takes the parameters as separate values, so it can inspect the actual sign. And in case x is positive, that is, stuff is happening on the right-hand side of the robot, or the right half hemisphere, then we use the standard inverse tangens. As soon as x is negative, we are using these results, allowing us to get up to 180 and minus 180 degrees. The problem with this is you see a huge discontinuity, which is if you are on the left-hand side of the plane, but you are moving between negative and positive fraction of y divided by x, where the result jumps from plus 180 to minus 180. We will talk about this in detail later. All right, for an example, consider this scenario here, and it's best if you pause the video and do the math yourself. In particular, compute the arcus tangens, output the orientation of the robot, and then the value of alpha. So let's start with the arcus tangens. The arcus tangens is given by the difference on x, which is a positive number, and the difference on the y coordinates. And you can see that it's around, like, let's say 50 degrees. And it's minus 50 degrees because the x-axis is here and the clockwise is the direction of negative rotation. So we write down minus 50 for the arcus tangents. The orientation of the robot itself is minus 80 degrees. So minus 50 minus minus 80 is plus 30. So we have to turn by 30 degrees. The direction of positive rotation is counterclockwise, so plus 30 degrees will give us a left turn from the perspective of the robot and will turn the robot toward the ping pong ball. In the second example, I put down 4 scenarios. In the first one, the robot is facing at 90 degrees, but x difference is 0 and y difference is positive. Let's assume that x is positive, so we can use the normal arcus tangens function. But now the x difference is 0, so you will find that the equation or the ratio between y and x goes to infinity. So you end up with half pi, which is 90 degrees. Now 90 degrees minus 90 degrees, which is the orientation of the robot, gives you 0 degrees. So the robot can just keep driving forward. The next example, the orientation of the robot is at 0 degrees and the y difference is 0. That means the difference between y and x is 0 always, so you are right here. So you are again at 0 degrees and the robot doesn't have to turn. In this case, the robot is at an orientation of minus 130 degrees, and the arcus tangents is about 120 degrees negative. So minus 120 minus 130 is around plus 10 degrees, so the robot has to make a slight left turn. And finally here, the robot is at 180 degrees orientation. It's looking to the left. The x difference is negative, so we are on either this or that branch of the II.4 function, and y difference is very close to 0. So here we have the problem that the result will jump back and forth between 180 and minus 180. The orientation of the robot is 180, so that means at some point it will tell it to drive straight because alpha is 0, and a moment later it might actually turn around a full turn. So let's look at this discontinuity more closely. And more often than not, you will have problems not when the robot is actually facing 180 degrees, but already before that. In this example, the robot has been trying to minimize its angular error to 0, so it started at 55, and then at minus 52, the arcus tangents function jumped, and the robot didn't think it has to do a right turn, but has to do a left turn because it has a large error of 300 degrees now. So what happened here, the arcus tangents function is around at 180 plus or minus. Let's say it's plus 180. The robot is at minus 130, so 180 minus 130 is 310, which you see here. But then once the estimate jumps to minus 180, it's minus 180 minus 130, and so you're at minus 52. So this is what happens. These things all add up, so the discontinuity happens even if the robot is not directly facing that direction, but the object is at the 180 degree orientation. Now, once this happens, the robot will turn into the other direction, but now the same problem happens. It tries to minimize its error from 300 down to 120, and then at 120 it jumps to minus 239. What's the reason? Again, we have 180. That is the direction or the orientation to the waypoint. Here the robot orientation is, let's say, 45 degrees, and so we have 180 minus 45 is around 120, which you see here. But if you have minus 180 minus 45, then gets you to 230. So what will happen? The robot will turn to make a right turn again and essentially go back and forth. So you can look at this again when it turns back. Same thing happens. We are again at around 50 degrees. It jumps to 300. And so the way to deal with this is, as soon as alpha exceeds 180 degrees, we want to subtract 360 to put it back into the range minus 180 to plus 180. And at the same time, if it goes below minus 180, then we want to add 360 degrees to put it on the other side. If you do that, the controller will work, and you can go all the way around the line following course. Now, how do we actually implement the control? What we will do here is we will follow our intuition to turn the error into wheel speed. And for this, I'd like you to look at this scenario here, where I have an alpha of minus 45 degrees. The robot has to make a slight right turn. This is minus 0.78 approximately. And now the question is, how do we set our wheel speeds to accomplish this? So in this case, I suggest to use the value of alpha directly. Alpha is currently negative. We want the left wheel to go forward, so we put a negative alpha here. This makes the left wheel speed positive. The robot turns to the right, especially if the right wheel is negative. So we take the positive value of alpha here, which will be a negative value in this case, and the right wheel will turn backward. What will happen if alpha is 0 in this scenario? Well, the speed will be 0 and the robot will just stop. So how do we make it drive toward the obstacle? Well, we would add rho to both of these values and it looks like this. Now the robot will turn until the alpha is 0 and then it will just drive straight forward until it hits the obstacle. Once you do these two things together, of course, you will combine turning and driving, so the robot will start driving forward immediately, but turn right due to this alpha addition here, and so the robot will drive in a curve to the waypoint. Now, we haven't talked about the error in heading, so if you want to plug in a final heading error, you can also add this to these equations here, so then the robot will balance driving forward, turning toward the waypoint and assuming its final position. In practice, it might be better to switch this behavior on a little later as you approach the obstacle. For example, you could say that as you approach the obstacle and rho is below a certain distance, you can add the tether E term and start turning the robot into the final location. And as the robot then arrives, this will be the only active term, and make sure the robot is adjusted correctly. So in summary, going from waypoint to waypoint is not just a key ability for a mobile robot, but it is essentially the way to implement any desired trajectory, be it for mobile or arms. The waypoint navigation is a two-step process. First, we have to compute some kind of error between the current and the desired pose, and then we have to turn the error into control signal. We have done this for a mobile robot using differential wheel kinematics. This can also be done for a car-like robot. It can be done for a robotic arm, and we will do some of this in next week's module.